at another kind of bond called a covalent bond, where two atoms get together and share their valence shell, like these two girls are holding hands. Some students get very frightened of these bonds, but they can be quite safe. The only elements that do covalent bonds are on the far right side of the table, and hydrogen, who seems to have no business being here. Some of the ones that do this covalent bonding do it with themselves, just like the twin girls holding hands. This can be kind of scary. These are the elements that form diatomic bonds. Notice it's diatomic bonds, not diatomic bonds, die! Alright, I've come up with several memory keys to help you understand the diatomic bond and remember the elements involved. You can call it brick cell phone, rhino cliff, hi no barf, see? Even Dominica birchloff. Or you can just shade these in on your table and try to remember those gases, liquids, and semi-solids should be written as pairs. Now we're going to look how to do the covalent bond, which really requires watching someone do it. Now, the first thing we're going to look at is a traditional bond using hydrogen and chlorine. So we are going to bond hydrogen, and hydrogen will be bonded to chlorine, which is one of the first bonds we did. The product will be called hydrogen chloride or hydrochloric acid, which is what's in your stomach. If we draw chlorine, we have 7 valence electrons and 1 empty spot. And again, remember, I'm the only person that bothers with the empty spot. When we get to hydrogen, we have only a single valence electron, so hydrogen will move the valence electron there. And we want the full and the empty facing each other to keep the diagram simple. Now what happens when hydrogen forms a covalent bond? Here, what we're going to do is it's going to form a bond with itself. So we put 1 electron here and another electron here. And again, this improper Collotti notation comes in handy. I'll put an empty spot and an empty spot. Now they do a sharing. Each hydrogen says, I want one, so it passes it to the middle, and the other one passes to the middle. And this is like putting it in a middle common ground. So we circle the shared pool of electrons, and they're here, and each atom can pretend like it has both, and we would write this as H2. So this is an ionic situation where this side becomes positive, this side becomes negative. This one is shared where they pop the electrons into a common center pool. Now, I've made a slight mistake here on the overlap. I only wanted to show the overlap in the center. So we're going to switch to another diatomic gas, fluorine. Now, fluorine has 7 dots. What we want to do really is clear the empties out of the way. In this situation, I typically put the empty one on the far side just because we need the pool of electrons we're going to share. Now, a sharing situation is pretty obvious. Each of these wants 1, so it will be willing to share 1. Or you can think of it as a tug-of-war between the two. Either way, this is what happens. One passes 1 forward to the center, and the other passes 1 forward to the center. The only pattern I'm showing here is whatever is convenient for the drawing. Now typically, we circle the center pool, and we circle the center pool here. Okay? And what looks like we have 1, 2, 3, 4, 5, 6, 7, 8 now for each fluorine. The mistake is don't count this guy twice. He's moved forward here. He's not there anymore. So this fluorine looks like it has 1, 2, 3, 4, 5, 6, 7, 8, and the same here. It's not very satisfactory, but it'll work. What happens when an atom that wants more than 1 shows up? So let's say we look at oxygen. Oxygen is missing 2. And a sister oxygen shows up. And this one is also missing 2. If you want 2, you share 2. That's the rule. So each oxygen will pass it to the center. Now, if you've left yourself lots of room, you can actually go forward to the center like that. If you don't, you can flare them out a little bit. But you understand, if you put the empties here, you're going to wind up doing sharing by diving in. The diagram gets obnoxious looking. So we circle all the originals plus the shared pool, and we circle all the originals plus the shared pool, and if you count 2, 4, 6, 8, you might count 10 if you forget that this is 1 electron that has moved forward. So we have 8 in each pool now. So this is why it's O2, and this is why it's F2. The shared bond is weaker than this bond because it's really not what they would prefer to do, but it will work. So if hydrogen shows up here, they may switch and form the ionic bond. Let's go one harder and switch to carbon. So I'm going to put carbon in the middle here and oxygen on either side. So we're going to attempt to form CO2. So we draw our oxygens, keeping those unwritten empties out of the way. You get them out of the picture. And we're going to do another oxygen here with the empty around here. Now carbon has 4 electrons. Where am I going to put them? He wants 2, he wants 2. Our best bet is to provide the electrons on either side. It doesn't really matter, but from experience, this is the best place to put the electrons. And we have an empty, an empty, and an empty, and an empty. Now oxygen wants 2. He wants 4. He's willing to lend 4. But if the person you're lending to will only lend 2 back, then they're the person that dictates the sharing. In other words, the cheapskate at the table dictates the sharing. Carbon says, I'll lend you 4. Oxygen says, I'm only prepared to lend 2. So carbon's like, well, then put your 2 on the table. That's all I'll do. So oxygen puts 2 on the table, and carbon reciprocates. Pops 2 over here. So this oxygen is now complete. It has a full octet. 2, 4, 6, 8. Its original 2 and the 2 it borrowed. It's done. It's happy. The carbon is not complete yet. It would like to share another 2. That's where the second oxygen comes in. This oxygen says, I'll share. And the carbon goes, not a problem, I'll share back. That's perfect. This oxygen is now complete. If we count the shared pool, and the carbon is now complete, and we get something that looks awfully like the Olympic rings. And I'm trying only to circle the shared pool. So this is how carbon dioxide forms. What on earth is with the splitting the electrons here and straight across here? It doesn't matter. This is what happens if your drawing is cramped. This is not cramped. If you put the empties here, you'll be having arrows crossing the page. So you'll quickly learn the best way to organize these so they don't become messy. The last example is going to be the formation of methane gas, which is CH4. Okay? So whenever you have one with multiple valence and another with not. So hydrogen is 1 dot, carbon is 4. Put the one with the bigger set of vacancies in the middle. It'll always work. We're going to put carbon there. And in this case, I'm going to color one dot on each quadrant of carbon. It really doesn't matter. And again, I'm going to put the empties in here just to make it clear what's going on. Now, he wants 4. I'm going to put a hydrogen out here. The hydrogen wants 1, and I'm deliberately putting hydrogens 1 there and the empty here. See what I've done? This is just to make the drawing neat. The 4 hydrogens that are going to bond will surround the carbon. I've already done this with you as structural chemistry in class. Now we're doing it with the Lewis dots. How do I know to do it this way? We have to tell you. You cannot predict CH4 yet. There are too many of these. We will give you the formula, and the layout is common sense. So how do we do this? Hydrogen says, I'm willing to share 1 with you. And the carbon will reciprocate with 1 this way. This allows this hydrogen to finish. But the carbon is not yet complete. What you have to do is go around this dial and finish it yourself. And this is where, of course, you pause the video and Boots the monkey will dance. And then you unpause this video and I'll show you the finished product to see if you got it. So magic, pause. Welcome back. Now let's see if you've got the drawing. So this hydrogen passes 1 forward. This carbon returns 1. And the hydrogen is done. So now you get the pattern. I'm just going to go around here, move these forward, make my circle, and finish the carbon. Forward, forward. Yeah, I did that one. So we got all 4 now. And I circle my shared zone. This is the kind of diagram you have to watch as it's made. If you're not in class that day and you haven't watched the video, these are a nightmare to learn from a book. But when you watch them created, they're fine. So we're going to look at one last thing before we're done for the evening. Because hydrogen is a funny element, it can form an ionic compound like this, which your stomach is full of, and a covalent compound like this, which your intestines are full of and are not socially acceptable to release in public setting, if you know what I mean. We call this natural gas, and it's in the pipes that feed our Bunsen burners. How can you tell when hydrogen is in its ionic form versus the covalent form? Really simple. Metals come first. We always put the leftmost element. So when we write sodium chloride for salt, sodium is to the left of chlorine. We never write it chlorine sodide. So when hydrogen and chlorine are written this way, then hydrogen is the left element and chlorine is the right. So hydrogen is positive, chlorine is negative. Notice here, hydrogen is leaped to the right side of hydrogen. Almost always, if hydrogen is on the right side of the formula, then it's sitting like it's in fluorine's table and pretending it's -1. If hydrogen is written on the left side of the table formula, then it's behaving like a metal on the left. It donates to become positive if it's on the left side of the formula. It receives to be negative if it's on the right. Right receives, left loses. This works out most of the time. But in general, we will have to tell you when we're dealing with a covalent situation. Anyway, that's the end of the lesson tonight.